We are talking about something different today. So the whole course has been on deductive calculi, which, are things you write down. They can be represented symbolically. Now, it's true, we're computer scientists, and most of these calculi I've talked about will be represented in a computer by data structure with sharing and so on. So I hope it's clear that if you've got something like these clauses in DPLL, you're going to use clever data structures to do it efficiently. Nevertheless, at least mathematically, it is a syntactic calculus. Now, these binary decision diagrams are different. So these simply are a data structure. Maybe a little context would be a good idea here. So in the 80s, I guess, people had some general theorem proving things. They were all symbolic. There was somebody called Stallmark who made some algorithm for theorem proving, and he patented it, which I think is a very douchey thing to do. Maybe he thought he would make money from it, but other people invented other things, and no one has heard of it anymore. These came out, I can't remember, maybe in the late 80s, and they made a big splash because this was the first time you could solve really big problems. And in particular, you could, hardware designs, in particular, you could verify just like that. So you could have, for certain things like binary adders, you could have mathematical specification of an adder, specification of your circuit design. Do they agree? Press a button, it says yes, or if it says no, it can actually enumerate all the places where it gives you the wrong answer. That was a cool technology. So how do they do it? It's a canonical form. I should mention what a canonical form is. So you've maybe noticed that if I take a formula and convert it into conjunctive normal form, we could get different answers, and yet they're all correct. They're all conjunctive normal form. That's because conjunctive normal forms are not canonical. There are multiple equivalent ones. Actually, the word normal form also has a meaning. So normal form is typically, you use that language when you are transforming a thing and transforming and transforming, and when you can't transform it anymore, you say it's in normal form. Somehow it's some kind of, all the bad stuff has been removed and you can't reduce it anymore. In fact, you're going to see this when you get the lambda calculus. They talk about normal forms there. Again, they are things that have been fully reduced, but maybe not unique. So the canonical forms are unique. And that's powerful because if I have two big formulas, maybe one is representing binary addition as mathematics, one representing the circuitry of an adder. If I put them into a canonical form, I will get the exact same thing if they are equivalent, which is exactly what BDDs are so cool at. And ultimately, these are data structures in a computer, and we use a lot of computer science tricks to make them efficient and so on. So the one thing that everybody gets wrong, this canonical form is based on an ordering. Now, as you know, we have propositional logic. Sorry, I should have said that very clearly. We are talking only about propositional logic here, right? No quantifiers. So the only freedom we have in our language is the propositional letters. In order to use BDDs, you have to put an ordering on your propositional letters. Now, if you're lecturing a course like this, you will use alphabetical ordering because that's natural. If you've got an application, it turns out the ordering is quite important and you might have to think very hard because that has a big effect on the performance. And if you change the ordering, you have basically a whole new ball game, as they like to say in America. So you have to, in other words, when you are doing BDDs, you are doing it with one fixed ordering on your propositional letters for everything you do. And if you decide you want to change the ordering, you have to throw everything away and start again from scratch. What else will we see? This is a shared data structure. And I guess this is where So I came in saying this is not a symbolic calculus like the other stuff. And that is because of the sharing. So you cannot write down, you cannot have a notation for a thing with sharing, because if you write things down, you cannot see with your eyes whether they're meant to be shared or not. Now, what can we do with these? Well, all of these claims at the bottom come from the fact that it's a canonical form. So if I have a tautology, and remember, tautology is a formula which always evaluates to 1 whatever interpretation you put on its variables. When you convert a tautology into a BDD, you will always get the same result, which will simply be 1. Likewise, if you have any unsatisfiable formula, and remember, they are formulas for which there is no way of making them true, no interpretation of the variables will make them true, and you convert them to a BDD and you get 0. And for other formulas, and again, if they are equivalent, you will get the same BDD. And because these are going to be completely shared in memory, we can actually equate BDDs with a single memory address, which is, if you like, the root of this data structure. Now, I'm calling them BDDs, which abbreviates binary decision diagrams. Funny, in the earlier version of the course, I called them ordered binary decision diagrams. And in fact, their full name is reduced ordered binary decision diagrams. Nobody calls them reduced ordered binary decision diagrams because it takes too long and you start to get bored before you get to the end of it. So we call them BDDs, but we are always meaning these reduced ordered binary decision diagrams. Now, this is simply a decision diagram. It's not reduced. Well, actually, it is ordered. It is ordered because I'm using alphabetical order here. And the idea is I start at the top, I have a simple propositional formula. And I'm just showing you all the combinations that can be. If you like, this is a different way of writing a truth table. P can be true, that's a solid line, or it can be false, that's a dashed line. Q can be true, solid line, false, dashed line. So you see this decision under Q is under the assumption that P is true. That decision under Q is under the assumption that P is false. And why did I highlight this one? I'm trying to give you an idea about the sharing. You see, this thing gives us a way to evaluate the formula for any particular value, because if somebody tells me, for example, that P is true and Q is false and R is true, and say, what answer do I get? I say, oh, P is true? Okay, you go there. Did you say Q is false? So you go there. You said R is true? Oh, the answer is going to be 1. That's what this thing is doing. And now you might note there's a lot of redundancy here, because this thing under R and that one, they're all identical. Now this one on the left is different, right? That's because of the highlighted 0 there. But all the others are the same. And so you might say, it's wasteful having these. So what you might be tempted to do is share up See, now what I've done, I've said I need a decision for R that if it's false, go to 0, if it's true, go to 1. But now instead of having 3 copies, I'm going to have 1 copy, and I'm just going to make everything go to that 1 copy. So I've saved a lot of memory. This is still not right, however, because, again, what did I say? P true, Q false, R true. So P is true, I go there. Q is false, I go there. R is true, I go there. I get the same answer. That's great. But why am I making a decision on Q? Doesn't make the slightest difference. It shouldn't be there. So now when you get rid of the things that are irrelevant, that is our final BDD. So it's reduced in 2 ways. Firstly, by maximal sharing, and secondly, by eliminating all the redundant tests like that one and that one. So now you might say, okay, it's trivial to make a BDD. I just make this full decision diagram and then I reduce it. And what is the problem with that? Well, if you're not sure, think of doing the same thing with 100 variables. So then you're starting with 2 to the 100 nodes in your tree, and you can see that's more memory than you have. Okay, so now is where it starts to get hairy. What we've got to do is somehow create BDDs from formulas without ever constructing the full thing that might need, what did I say, 2 to the 100? That is something like 10 to the 30th or something. That's a lot of memory. You don't have that much memory. Anyway, so we need to do it directly. Sorry, we need to kind of immediately generate this thing out of nothing without ever generating the full thing. And there is, by the way, a really cool thing about BDDs. This is the only technique we have which can work with weird logical symbols like exclusive or if and only if, directly. This is a big advantage. So you may remember that if you have if and only if for all of our previous techniques, you've had to expand it out. And that immediately causes an exponential blow-up. Exponential blow-ups are bad, but luckily it's just the way BDDs work, they can handle these directly, and that maybe is one reason why they were so great for hardware. In hardware, you've got exclusive ORs all over the place because that's how you add, right? And previous symbolic techniques were just completely useless for things where all you're talking about is lots of exclusive ORs. So we will be working directly with our logical connectors, even if they are these. And yeah, if you expand them out, then you will certainly lose marks because you did a bad thing. And our method will be recursive. So, of course, formulas have a recursive structure. We will recursively convert the subformulas to BDDs, which you should imagine as being laid out in memory already, maybe sharing with lots of overlaps. And then what we need to do is join those two BDDs together using whatever logical connective happens to be at the top, kind of combining them, even if it's exclusive OR. We combine them in such a way that the new BDD gives the right result and respects the ordering of the variables and is maximally shared. And here's where it starts to get hairy. Is this thing, are you going to work? Does it work? You know, people dump all their rubbish on top as though, don't know what their houses look like. We will see in a moment if I can get this one going. So this is the paper version of the algorithm, but it doesn't make a lot of sense. I'm just doing it so I can have something in the notes. So if you're dealing with negation, that means, and I'm calling it Z, I'm using Z to refer to actual BDDs. So the idea is I've created a BDD in memory for a formula. Now I want to make the BDD for the negation of that formula. How do I do it? Actually, maybe the answer is easy enough. Your BDD for your original formula has a 1 at the bottom for things that go to 1 and a 0 at the bottom for things that go to 0. And all you've got to do at the very bottom is exchange the 0 and the 1 because that will be the negation of what you started with. This is an equivalent way of saying that recursively. I don't know if it's very clear, but you know, this This is a thing. Yeah, and you do need to make a copy of the BDD because you don't want to spoil the original one, which somebody else may be using, because this is a shared data structure, right? So you have to make a copy. Now, it will turn out, I told you that we can deal with things like if and only if directly. That will mean that if you are dealing with if and only if, and one of your operands happens to be 0, then you will do exactly the same thing as with negation. Now, I will need to do a demo very soon, because here is where it's not only incomprehensible, but this can't be there. Not strictly accurate either. So this is just giving you an idea. So I have some binary connective, and I've already recursively converted the operands to these diagrams. So, and indeed, if one of the operands is a 0 or a 1, we know what to do. So I just told you, if we have if and only if, or something like exclusive or, then or in the case of if and only if in particular, I told you to do the thing on the previous slide. For and or, we know what to do because, anding something with 0 will just give you 0 and you're finished, and so on. In the general case, again, this is not very helpful, but what the main thing I want to highlight here is your BDD will have a branching on some variable at the top. We can call the variable of the left one P. The variable of the other one may be different. It might be some P prime. Now, there is the easy case, which is when they are testing the same variable. Because if you think about it, the result, if we are anding the two things together and they are testing the same variable, then we know if that variable is true, each of them will go to the true part of their BDD, and what we need to do is recursively get the BDD for anding those things together, and that will be correct. If they are, if both P and P prime are false, then we will both get the Y part here or the Y prime part there, which are when they are false. So they will both be false, so we are going to and the two together. It gets maybe a bit messier when the variables aren't the same. And this is where, okay, this is a correct formula, but I have, for doing it yourself on paper, I have an easier way, which I will show you. I mean, you can see if that thing on the slide makes sense, but I will show you an easier way. But first we need that. Right. So first, a baby example. And actually, you may notice, I think there's some careful wording on some exam questions. Sometimes they will say, write down the BDD for a particular formula. And that is a hint that all you have to do is write it down. But then the evil ones will tell you to calculate or show the construction, in which case you actually have to show how you do it. So if I have the formula P or Q, and throughout this lecture, the ordering will always be alphabetic. To make a diagram for P or Q, maybe it's obvious that the only way to get false is if both P and Q are false, and every other combination gives us true. So if you test on P, and if the result is 1, you get 1. If P is, however, false, you test on Q, and if it's 1, you get 1 again. In other words, you maybe should be able to write this down without even bothering with anything. And certainly the BDD for a single variable like P, it can only be this, right? If P is true, it's true, right? So that's the BDD for a single variable, and There we have one for this teeny tiny formula here. Now, this is where I can see why people start to make, okay, let me do that one. So, and are you working? Incredible. Okay, so if we want to do that, so there we have a P with going to 1, and if false, we go to Q, and it's like that. And the other one is Q going to 1, and if it's false, we have R. Okay. Whoops. And we want to combine them using implies. Now, I told you that the case where when the variables are different is a little more difficult, and there is a way of cheating which you can do. You can do it on paper. Of course, the computer would never do this, but what we can do on paper is to pretend there was a test on P after all, and just kind of insert a redundant test. The point now is I've made the variables the same, and now I think it's a bit more intuitive what we should do. So, and this is why I call it the two-finger method, because you put a finger on each one, and you say, I'm going to make the result. The result will probably begin with a test on P. So I will write a P over here. Is that visible? Yeah, it's just about visible. And now I'll ask, what is the true case? If P is true, that takes me to 1. If P is true there, that takes me to that thing. Okay, what is 1 implies anything? It's the same as the anything, right? So 1 implies A is A. Therefore, if P is true, it goes over there. What happens if P is false? So we go back to the top. P is false. P is false. I have a test on Q. Now we have to do the same thing with Q. What happens if Q is false? Q is false. I have 0 implies something. Remember, 0 implies anything is true. So if Q is false, it goes to 1. Hope I'm right. Now we go back to Q, and now we're looking at the case where Q is true. That goes to 1. That goes to 1. So if Q is true, it seems it also goes to 1. Which seems to imply that I should simply have, if P is false, it goes directly to 1. Now, what is the actual answer here? So if P is false, it goes to 1. If P is true, it goes to the same thing as over there. Okay. So this is an awful mess, though much less than the mess I found when I came in here. And this kind of reflects what will happen in the computer. The problem, even with this diagram here, is it does not show the sharing, because this and this are the same in memory. Now for something really horrendous. Now, if this was a nice exam question, which I can't remember, though I did set the question, but it was a long time ago. The question might allow you to write out the BDDs for the two operands directly. And how would you do that? You'd say, well, it implies. So clearly, if P is false, it goes directly to true. That's trivial. If, on the other hand, P is true, the only way it can be true is if both Q and S are true. So you get, if P is true, you go there. If they are both true, it goes to true. All the others go to false. So I think with a little practice, you should be able to go from there directly to this if the wording of the question lets you. As for this, the thing that will trip you all up, and probably I was evil and deliberately wrote the formula that way, because if you convert that directly into a BDD, you have to remember your alphabetic ordering and not test on S first because it was the leftmost thing in the formula, but you have to choose the thing that is first in the alphabet. This is maybe slightly trickier, but if R is false, why is it true? Because if R is false, that will be true, of course, and if R is true, it will be S. See, the second part here is simply S. If R is true, it's S. If R is false, it's true. Okay, so you could write those down without doing any work. And now, so let me copy them and then see if I can do the rest, because it is actually a bit of a pain. P, Q, S, 1, 0. So what is Q doing? It's true is there, and false is there. That's barely legible, he says. And where is, yes, and that is, okay. And the other one, which is RS and S, okay. That's a 0, a 1. Okay. So as I said before, in order to use the two-finger method, by the way, computers never use this method because they don't have fingers. I'm going to have to put in 2 dummy tests. And see, and what is the opera? We're doing and, right? We're anding them, is that right? Yep. So, and I know this is going to be just awful. So if P is false, it goes to 1. If P is false here, it goes to that. So 1 ANDed with anything is the thing. So I put a P here for the answer, and if it is false, it goes to that. What happens if P is true? Well, we're going to have a test on Q. So now Q can be false or true. If Q is false, it goes to 0. Okay. What happens if, oh God. If Q, this was really nasty, because if Q is true, I actually, how do I do this? It needs to go to R, which in both cases goes to S, right? So if Q is true, it will go to R. This was a really nasty question. If R is false, that is 1. That is going into the S there. So if R is false, it's going into that, which is actually the same as this. Actually, can I just make it into that because it's a bit closer? And if R is true, that goes to S. And if R is true, that goes to S. Looks like they're both going to S. Am I finished? I think I'm finished. Let's see if that agrees with what's on the slide here. And I hope it does, although you never know. So P, and I forgot to say, this thing is a redundant test. So this is a really tricky thing. If you use the two-finger method, you see you have to get rid of it again and copy it out, because in fact there is nothing there. It is actually going down to that. So going to R there with that bit of fixing there, going to S if true. 1, yeah. Yeah, I think, wait a moment. There's another redundant test, I think, here, because, yeah, true and false are both going there, so that should, in fact, be going directly. Yeah. So, and actually, this is what people do. They make a really messy thing, and then they clean it up to give that as the result. I'm asking you to show all the sharing would maybe be going a bit too far, because it does become an unreadable mess. The main thing is that it has to be fully shared here. So you see, anybody who had 2 copies of this, for example, would have lost marks because it is meant to be shared. I don't have a Dilbert this time. Okay, some remarks about this 2-finger method. Remember the variable ordering. I so often, marking these things, I see students somehow getting in a tangle, and then you see maybe they're testing on P, and then they're testing on Q, and if you're testing on P again, it's gone wrong. Right? Tear it up and start again. This thing about this redundant test, you can see I got into some trouble here because I put them in, and this is kind of really messy here, and then you have to take them out again. So it is tricky, and we should be glad that computers can do it for us, of course. And God, this reminds me, do they still teach you Karnaugh mapping in digital electronics? Oh, yeah. See, when I learned this in the 70s, and it was already obsolete then, right? The purpose of Karnaugh mapping is to help you build computers when you don't have computers to do this, in that case, trivial minimization of formulas. Of course, this technology here, already by the late 80s, is infinitely more powerful and allows us to reduce things to a minimum form. I should mention some of the tricks. So I've kind of said that we're maximally sharing things. And I hope I've said, I need to make it clear, anywhere in our system where we have 2 copies of equivalent formulas, not syntactically identical formulas, but equivalent formulas, they will all, when they are converted to BDDs, get mapped to one single machine address. So this is a canonicity. It's really very powerful. That means that whenever I want to simplify a thing, like if I've got a redundant test, all you have to do is check, are the 2 addresses the same? Or if you are simplifying a conjunction, you want to know the case where the 2 operands are logically equivalent. Well, it's only if the 2 addresses are the same. Now, there's a separate thing. Now, these 3 points here are all about the canonicity of the data structure. The last point is merely an optimization. It is merely a fact that you will often, when you are computing BDDs, reconvert the same formula over and over again, or you will be asked to convert the same formula. And if you can keep a hash table of things that you have already seen, then you can map directly to the existing BDD, because if you don't keep this hash table, you will eventually, I guess, discover that the thing is there, but you end up creating the whole thing and at some point later on sort of discovering that they are the same. So it is much more efficient to hash these repeated computations. I think some more historical context might be useful. I mean, I've been lecturing this course for so long. This is the last time, by the way. I've been lecturing this course for so long, and so much has happened since. So the original DPLL is a very, very old thing. So resolution came out just slightly after. But sticking now to propositional logic, BDDs made a big splash on the scene already in its ancient history now, 1986. And they were quite dominant until about 2001 when they revived SAT solving. Remember, DPLL is SAT solving, but they revived it. They made it a lot faster. And now, by 2001, we suddenly had two very powerful methods for solving propositional problems. So you now maybe have to decide which one you want to use. And it's worth bearing in mind their differences. So BDDs are giving you a full representation of the truth table. A SAT solver will give you one counterexample at a time. BDDs can handle full propositional logic directly without any transformations, whereas SAT solvers need normal form. Now, it seems to be that BDDs are still very good in certain hardware applications, also in things called model checkers, which I think you get a glimpse at next year. I think those SAT solvers are much more commonly used now because, in particular, the SMT stuff I mentioned last time. And I believe I mentioned this phrase to you before. This counterexample-driven abstraction refinement is when you try to check something by starting with a really crude abstraction. Think of a massively pixelated image. So you take a really crude abstraction, it might flag up a thing you should worry about, and then you can try the claimed counterexample on the real problem. If the counterexample turns out to be a bogus one, it can tell you exactly how to refine your abstraction to make your image slightly less pixelated until you finally arrive at a thing which models your thing enough for it to get a real counterexample, which is a real bug in your program. This is quite a powerful technique. Reminds me of a thing. So, guy named Byron Cook, actually I'll write his name down. Byron Cook, who used to be at Microsoft and is now at a very small online shop called Amazon, has an automated reasoning blog, which I believe Google will find for you. And he just did a new post yesterday about SAT solving in which he compares the performance of SAT solvers from 2001 up to today, normalizing it for hardware speed. So, of course, we need to ignore, we need to correct for the difference in hardware performance. And still, today's systems are, I think it was 3 times faster or something, on handling much bigger problems. And also we now have a scope for parallelism at a very high scale, which we didn't have before. So it might be interesting to look at. Now, a remark about the variable ordering. So this formula here, when is this formula true? It's not hard to see that for this formula to be true, you need a P and a Q with the same subscript to be true, right? So if, for example, P1 and Pn are true, we know the answer. But it could be anywhere, P2 and Q2, etc. Any one of them can be true. We know the answer. Now, let's use this variable ordering. So this is maybe not alphabetic. It's not alphabetic, right? We're looking at the subscripts first. And then we get a BDD. Oh, I haven't actually told you what the BDD is. Well, I can write it down for you. So we test on P1 if it's true. We test on Q1 if it's true. The answer is true. If either is false, we test on P2. If it's true, we test on Q2. You get the idea, right? That will be a linear space BDD that will have exactly one test on each of the 2n variables. What happens if we choose this ordering instead? Well, I used to try and draw it, but I don't anymore. There's a BDD package that does it for you. How many variables have we got here? 4. Sorry, yes. N is 4, right? That's not very pretty, is it? Okay, so in general, if you're using BDDs, clearly if you've got a large problem, what you typically will do is look at things that are related. So you say, well, there's a big connection between the P1s and the Q1s, and so you put them next to each other in the ordering. And that is how you get compact BDD. Now, in general, this is a hard problem, and I know some people put a lot of effort into trying to figure out how to do this automatically, which I suspect is not really very feasible. Anyway, that's it for today. Thank you.